What is the relationship between time domain and frequency domain in terms of basic parameters? We will answer this question in the next minutes and provide you some expert advice on vibration monitoring here at Intelligent Machine Monitoring. In this episode, we talk about the correct rules to capture a usable time domain signal. You will learn how to compare and make correct settings so that you will not miss any frequency of interest. My guest today is Ramnek Sharma, a certified Cat3 vibration analyst. Welcome, Ramnek. I'm glad to have you here and that you share some of your valuable knowledge with us. So the stage is yours.
Okay, so baton is in my hand. Before I start sprinting, I would like to thank Joost, my colleague, for providing me an opportunity to express or to share my know-how with you guys through this video. So let's get started. Today, as we know, time signal is basis of all the analysis. Means, in other words, all the analysis plot like envelope spectra, FFT spectra, time synchronous averaging spectra, all are derived from time signal. Time signal give you much more information than any other plot because it's a root of your analysis. In fact, in some cases, if we compare time signal with FFT spectra, time signal reveals much more clear indication or gives much more clear hint of the problem. To explain or to validate this statement, I will take two examples. Herein, the first example is a machine that is out of balance. The time signal looks very sinusoidal and FFT has a dominant 1x turning speed frequency. In this case, both these plots give you a hint of unbalance. Okay, it's fine. But in second case, there is a fan driven by a motor via a belt drive, and this belt has a localized fault. And whenever this localized fault passes over the pulley, it will create a transient like this, and like this. So it is clearly visible in the time signal. But if you see the spectra, it's a bit, I need to put too much of brain what's going on with this machine. It's really important to look into the time signal, and in second example, time signal give you a clear picture what's the problem in the machine. There are some other examples where time signal has an upper hand to diagnose the problem, like gear monitoring, like a slow speed bearing monitoring. Time signal plays very vital role. But there is a basic challenge. The challenge is to capture an accurate or a correct time signal. In other words, to capture a time signal that must contain a frequency of your interest. So frequency of interest means if I am looking at the BPFI, ball pass inner race frequency, so I should capture a time signal that have this frequency there. Okay? As a fact, we know that any vibration sensor gives you an analog signal. Let's have a look on the flow chart or a flow diagram how we derive a time signal. As it's a known fact that any vibration sensor gives you an analog signal or generates an pure analog signal. This analog signals have all the information what we needed, but nowadays this analog signal is converted into digital form via A to D converters. And this, why the digital form? Because digital form is easy to manipulate and also easy to store. That's the reason why we convert this analog signal into the digital form. Digital form is nothing but reconstructing of this analog time signal by joining the discrete dots to form a shape of your analog signal. So maybe if it is clear, these are the dots which we join to form or reconstruct the analog signal. And these dots are called samples or number of samples. number of samples. Okay? And the rate at which these sample is been captured is called sampling rate. Means how fast these samples are being captured during a process of A to D conversion. And this is called sampling rate. So now we have two parameters for time signal. One is number of samples, these discrete points, and the sampling rate, that how often or how fast these point has been captured. So this is number of sample and this is sampling rate. And the third parameter is a time frame or a time window, how long this time window is. So it's a time period. Time period in time domain. So we have three parameters in time signal. One is a time period, second is number of sample, and third is the sampling rate. And these all three parameters share a relationship. And what is that relationship? It's T is equals to number of samples divided by sampling rate. Okay? Now there are some rules for each of these parameters so that you can end up with the correct settings. If you follow these rules, I'm sure you will be able to capture a real good signal and you will not miss the frequency of your interest. Let's go one by one to these rules. Let me rub this first. Okay. So first we put in this formula again. Number of samples and sampling rate. So the first rule is for sampling rate that it is a Nyquist theorem and it is known by most of you guys. It says that your sampling rate should be greater than twice the frequency of your interest. It means your sampling rate is greater than twice the, or you say twice the frequency of interest. So this is the first rule. It is very, very important rule. If you don't follow this rule, you end up, or in fact, I should say it differently, to avoid aliasing, you should follow this rule. If you don't follow, or if you capture a less number of samples, then you end up with a frequency in the spectrum which is not present in the machine. So it is a aliasing is an error that occurred because you are not following this rule. About aliasing we will talk or we will discuss in next videos, coming up videos, but this is important. This is the first rule, that your sampling rate should be twice greater than your frequency of interest. Okay, first rule. Second rule, for the time period, your time period should be at least able to capture 6 shaft revolution. Okay, 6 revolution, at least minimum of 6 revolution you should capture in the time signal. So, and the third is for number of samples. Number of samples is always a 2 to the power, like for example 2 to the power 8 is 256, then 2 to the power 9, 512, 2 to the power 10, 1024, 2 to the power 11, 2048, 2 to the power 12, 4096, and so on. The rule says that you should capture minimum of 2048 samples. Minimum. 4096 is better, but minimum you should capture 2048 samples. Let's have an example. My machine is running at 755 RPM. So it means it's 29.7 hertz. And one rotation, one revolution would be covered in this much of time, 0.034 seconds. As a rule, what we said, you should capture minimum of 6 revolutions. So, how much time you need to capture 6 revolutions? 6 multiplied by 0.034 seconds. So, it ends up with 0.205 seconds. Okay, correct. What is the formula? Formula says T is equals to N by Fs. So you have a time, you have a number of samples, as we said it is 2048 or 4096. This is better, but minimum you should take 2048. So what's the time? 0.205 seconds and 2048 samples. And Fs you can calculate. So Fs is 9984 samples per second.